Hey everybody, hopefully you're doing well today. This is Adam Ward, and I want to talk to you today about particular solutions. This lecture goes along with Lecture 4 in your Chopra textbook. So in Lecture 3, we talked about the general solution, and we said the general solution describes the behavior of the system when W equals 0. You'll notice that I made a mistake putting my slides together there. It's not the steady state behavior, right? In fact, it is specifically the non-steady state behavior. This is how the system works when W equals 0, so how it recovers from a load in the absence of any loading. And what I want to go through today is the particular solution, which describes basically what happens if W isn't 0. And so if we take the equation we had in Lecture 3, the modification that we're going to make today is we want to find solutions when dc dt plus lambda c is equal to something. And we're going to do that by looking at some idealized cases for loading. So the first case we'll take a look at is what's called a pulse loading, or an instantaneous loading. We'll commonly use this to describe spills. Sometimes people call this a spill response model. And so the idea here is that our loading looks like I've drawn in red in the top right of our screen. It's 0 with the exception of one period in time when a given mass is instantaneously loaded into the system. Okay, so what happens? Well, in our CSTR, which is perfectly and instantly well mixed, as soon as you add mass, the entire system instantly comes up to a given concentration. And we'll call that concentration, it comes to C0. And as soon as that mass is released, we get to that concentration, the load is gone. And so the recovery then is going to look more like an exponential solution. Mathematically, this is called a Dirac delta function. You would write it like this, strictly speaking, where that lowercase m is representing the mass of spill into the system. And so if we separate variables and solve, we can find that our concentration through time is still described by a simple exponential decay, and that C0 is simply calculated as the mass per unit volume. So what will it look like after the spill? It's going to look like exponential decay, and how it decays is going to be a function of that eigenvalue, right? That characteristic lambda that describes the outflows, reactions, settling, other processes that remove mass from the system. So exponential decay. We already knew how to deal with pulse loading. We just didn't do it formally with Dirac delta functions and go through the mathematics of it. One thing to note here that T is kept track of in this case as time after the spill. And so you're defining that T as time elapsed from the release, or from the Dirac delta function itself. And you can see I've drawn in green what that looks like on the graph. The next kind of load we'll take a look at is a step load. And the idea of a step load is that loading was equal to 0 until some point in time, the dashed gray line that I've drawn. And at that time, the loading jumps up to some steady state load of W. So it's a stair step. Now, what does the system do? Well, we know that before the load, there was nothing happening. W was equal to 0, so concentration should also have been equal to 0. And we know that if enough time goes by, we should achieve a new steady state. So the goal here is to connect these two dots. The mass balance equation then looks something like this, where that W really becomes not a function of time anymore as long as we're working to the right-hand side of the gray line. So we're working greater than T equals 0. Separate variables and solve, and we get an equation that looks something like this. So the concentration time series is equal to the loading rate, W, divided by that eigenvalue lambda times volume, multiplied by the quantity of 1 minus e to the minus lambda t. Don't memorize it, but do recognize that that's the form associated with a constant load or a step load. Now, what does that look like? Basically, it's an exponential growth of concentration until you achieve that new steady state. So one interesting extension of this is you could say, well, can't I use that to help me learn about the long-term steady state of the system? And so as time approaches infinity, meaning that exponential gets to be an incredibly large but negative number, that right-handmost term functionally drops out. And so if that drops out, you can calculate the steady state concentration as W over lambda V. Right? And so you can see I've illustrated this now on the graph. And we represent that with as a C with a bar over top of it, or an average concentration in the long term. Now, what happens if the initial concentration wasn't zero? So a case something like this, where you do have an initial load and you've reached an initial concentration, and then your load steps up partway through, no problem. You can combine those two solutions. So you simply have some initial concentration, C naught, that was due to some initial load, W naught, and you add to it the solution for the new step load. So point here, solutions are additive. If you've got multiple loads coming at different times, different amounts, you've got a step load and then a spill that occurs 30 days later, you can handle that. You just have to add together your particular solutions. And we'll do examples of this in the classroom as well. Yep, and there will be at least one example in your homework. Okay, the next load I want to take a look at is what's called linear loading or ramp loading. And the idea here is that our load increases linearly through time. So something like I've drawn in the top right, where this beta L is describing the slope of that loading rate, or the load per time that will be applied. Mathematically, it looks something like this, where our loading term is now described by that beta multiplied by t, so that's a linear growth of the load itself. We can solve that equation to get our time series of concentration, and I want to focus you on what this actually looks like. And there's a figure in your textbook that shows this as well. So in the bottom right panel, picture these two parallel lines that I've drawn with red dots. Right? Think of the top one as the loading. That's exactly timed with loading. And think of the bottom one as lagged behind that by some amount. So we can conceptualize that at early times, the system is starting to respond to that load. But eventually, the system just gets overwhelmed. It can't act on that load anymore, and its concentration starts to just go up as fast as we are loading. So that's that late time piece that I've circled in blue. That lag time is 1 over lambda. That's a characteristic time of lag between your loading and when you hit that sort of steady state increasing slope of concentration. And finally, we're going to take a look today at exponential loading. And so the idea here is that perhaps we have an exponentially decreasing mass loading rate. So illustrated in the top right, we've got no load, and then at some time, t naught, we have the load go up, and then it decreases exponentially through time. So that's not the concentration decreasing exponentially, that's the load decreasing exponentially. Mathematically then, it looks something like this. And again, I'll spare you the calculus, but you can go through and solve this equation to get what I've written on the bottom left here. Now, I've presented this to you as though it's exponentially decreasing. And you'll notice in the bottom of your slide that I've written these as plus or minus beta E, plus or minus beta E in this term and in this term. Right? And the reason that I've done so is that the same equation could be used if you had an exponential ingrowth of loading. So for example, if your loading starts out at 0, and then it grows in exponentially, you can simply use the plus version of beta E instead of the minus version of beta E. Now, what does concentration do here? And this is shown in red going with the exponentially decreasing load. You get concentration ingrowth to a point, and that load is continuing to go down, 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 down through time. And so at some point, the system can actually remove more mass or remove mass more quickly than you're adding it. And so your concentration comes up to this peak. We refer to that as the critical point in the system, and we have an interest in being able to calculate the critical concentration and the critical time. Right? Why is that? That's the worst case scenario for the lake. That's the point where you get the highest concentration, and potentially that's the point where you're having the most risk to the ecosystem or to human exposure for that pollutant. So we've gone through 4 different types of loading. If you read your textbook, there is also sinusoidal loading, and there may be a couple more complicated loads even beyond that. We're going to focus in this class on the ones that I've covered in this lecture video. So I don't care if you spend the time on sinusoidal loading or other loading patterns. They're very, very similar. It's just the calculus that takes you from that mass balance equation to the explicit solvable equation that changes. So by watching this lecture video, you ought to be able to deal with pulses, step loads, ramp loads, and exponential loads, as well as recognize that you can use these to combine solutions for more complicated scenarios, such as a linear load and an exponential load happening at the same time. I hope this video helps, and I'll see you in Lecture 4 in class. Thanks, everybody.